Hello and welcome. I decided to investigate Metal CPP, that is the macOS Metal API for graphics running on the C++ header. I guess as an overview, I'll start this by answering the question, why Metal? Now, I'm sort of platform agnostic. I'm language and API agnostic. I think we can only benefit from the cross-pollination that comes with seeing how to do something a bunch of different ways. And so in that sense, it's sort of a no-brainer for me. I actually got a Mac just because I was interested in Metal. Why climb Mount Everest? Because it's there, right? For those of you who are not familiar, Metal is basically macOS's next generation low-level graphics API. Gets you as close to the Metal as you can. Now, I personally, I'm sort of on the fence. I was not necessarily one way or the other with these Mac machines until the M1 came out, and then I was just blown away by the capabilities. So if you have a Mac and you want to do graphics programming, you want to get the most out of your hardware, Metal, strongly recommended. Now, so with that out of the way, I want to investigate the structure of our program. I'm going to be using AppKit, basically, the Cocoa application environment, and there is sort of a specific way that things are going to be done. There's sort of no way to explain it. The best way to explain it is just to draw a diagram and speak through it. So here's how the app that I build is going to run. Okay, so the top level control is going to be a next step application class. This sort of kicks off the main loop, gets things started. Now, if I want to add my own behavior to that application, the default or the best practice way to do that in macOS, in AppKit, is to create what's called a delegate. Okay, so that next step application will own a next step application delegate, and this will be where more of the behavior will actually be implemented. Now that next step application delegate will own a few other resources. We'll have a next step window, a MetalKit view. MetalKit is a package which makes using Metal a little easier, has some good quality of life, like some time savers. We'll also own a Metal device. Now, a Metal device more or less abstracts all of the logical things that we can do with our graphics card. So it's sort of like the main controller for everything Metal related, and it's sort of like basically the graphics card device. So its closest equivalent would be the logical device in Vulkan. So all of this stuff is set up, but the next thing I want to do is I want to have another delegate which will handle the actual drawing. Okay, so I'll have this MetalKit view delegate, and this MetalKit view delegate will be registered as the view delegate, which means that every frame it will accept a signal to redraw the view on the screen. And then this will have our custom renderer class, and it's finally at this stage that our Metal programming happens in earnest. So for a lot of this code, I've adapted the Metal CPP sample, which is on Apple's webpage, on their learning resources. So I'm adapting that code base, but then for most of the series, we'll be doing a lot of work here, implementing our own Metal rendering code. So the goal of this series is to sort of build up a small game engine. Now, I'm not doing anything crazy. We're not making like a massive editor. We're not rebuilding Blender or anything like that. So just nice and simple, nice and small, but it is going to be data oriented. And there's a challenge that comes with that. And the challenge is that This app is going to be using the MVC control design pattern, Model View Controller. On the surface, it may not seem like it matches with ECS, but there is sort of a split up. So here's how I'm going to organize it. The model in an MVC app is the underlying data, basically. So here we'll have all of our components. And if you haven't seen a data-oriented ECS system, don't worry, we'll be talking about this, but the components are basically all of the raw data that we're going to be working with. So this is all the raw data we're going to be working with. We are going to have maybe a factory class to make some various objects, and we're also going to have probably some update systems. Okay, so this is all kind of termed under model because we think of it as like the underlying ground truth of the program. It's the underlying database that we're going to be working with. Now, on the other hand, we'll have a control section, and this control section will basically be our delegates and our app, really. So like all of this stuff, really, that's all the control. It goes from a top level control down to more fine-grained control. And then finally, we'll have our view. And for the view, we will have some various asset loaders. So asset loaders and factories to load various things, load in shaders, I guess, load in models, textures, all that stuff, anything really needed by the renderer. And then we might have some rendering system, or possibly a number of systems if we're doing multi-pass rendering or something like that. That's the basic overview, sort of where we're going. Don't worry, we're going to be going super slow. So today, all we're going to do is load up, get a C++ project up, get the boilerplate code in, get a solid color on the screen, and investigate that. So let's have a look at how we will set up a C++ project. All right, so let's get this show on the road. So first thing I'll do is I'll just open up Xcode and I'll make a new project. I'll make this a command line tool. And I'm going to call this, I don't know, who cares? Hello Metal CPP, doesn't matter. Okay, we'll set this up, make sure the language is in C++. We'll just go next. We'll have to save this somewhere. I'm going to put this, yeah, why not? I'll put that in my CPP folder. Okay, so there are a few things that I need to do. I'll close this down for now. Now what I'm going to do is I'm going to write a few define statements. Now these define statements need to be written at some point only once in a translation unit somewhere. So I'll go ahead and put these in. So again, it's stock standard stuff. They need to be in here at one point in the program somewhere. And now what I'm going to do is I'm going to include a bunch of header files. So Apple has provided various HPP headers. They're bindings to underlying libraries. So if we look at this, we have metal.h. We want metal HPP, which is the C++ header, but we're getting some errors. So I'm going to need to tell the project where these things are. Now, if I go to my dev folder, I have this downloaded, and in the code that I provide, I will provide this package as well. So this is metal CPP, this folder here. Inside, we have all of these things. All very useful, you know, AppKit, Foundation, MetalKit, Metal, and these are the HPP headers that I want to link to. So what I'll do is I will just right click here, go get info, and then right here, where are we? Where? I want to grab this and copy it. Okay, I can close that down. And now I'll just go to my project. I'll go to build settings and I'll search for its header search path. So if we go header and then down to search paths, we have this header search paths option. Open that up. We have two of these, debug and release. So I will go ahead and add this to both. So I want to go paste that and then slash metal CPP, copy this over. So no matter if I'm running this in release or debug mode, I have access to it. Okay, so I can close that down. And now, fingers crossed, the error goes away. Okay, excellent. Okay, cool. So I've included the HPP headers for all of these packages. Now, if I go and run this might actually be okay, but I'm just going to quickly talk about some things. Let me just run this right now. Build failed. Okay, so this is not great. Not great at all. What I'm going to do is I'm just going to go to the project and I'm going to look at build phases. And it's right here, this link binary with libraries. So I need to add the libraries that I'm going to use. I've got the headers, but they don't know what they're linking to. So that was MetalKit framework, AppKit framework, and Metal framework. Okay, cool. So that, let's see if that fixed it. Okay, it runs, does give us a warning saying non-portable path. So what this means is if I take this code and I copy it over to some other place, then it's not going to keep a relative path. So what we can do, okay, I'm probably going to, I've spent a bit of time working on this. I'm probably going to edit this out. So, boop, 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 step back in. Here's where we are. So I rejigged the layout so that this was portable. What that means is now if I copy this project anywhere, the Metal CPP will copy along with it. Now the layout here is I have this Metal CPP folder that has all these headers and things that I need. That is in the project folder, separate from the source code. And now to link to that, all I need to do is go to the header search paths. And here I'm using this macro project directory / metal CPP. And we can see, hopefully we can see here that this is the path which is linking, it's referring to that folder there. So then in the source code, we can just use it like this. And the system finds it. Okay, great. So we can just double check, run this, and it's working. I dislike this. What do you mean non-portable? It's working. It's fine. Okay, so we have that. Now, one more thing, and this is just a Metal CPP requirement. But the language dialect for C++, if we go to build settings, dialect, Apple CLang language, needs to be 17 or higher. So I'm working with 20. This should be fine. And yeah, so there we have it. That is our base project configured. Okay, so we have our program up and going, up and running, the skeleton. We got no errors. We're ready to put in the boilerplate code. But before we put in the boilerplate code, I just want to talk about something that will explain some of it. So with Cocoa apps, they use one of two memory management modes. So obviously in C++, usually everything's all manual. You have to, go new and delete to create and destroy objects. But in Cocoa, objects are reference counted. There's a system which operates under the hood, which controls the deletion of things. And that reference counting is either automatic or manual. Now, the thing is with Metal, we want as much performance as possible. And so Metal uses manual reference counting, which, it's it's not too bad once you get the hang of it. So with manual reference counting, every object has a reference count, and that reference count is incremented when basically one of two things happen. Either we allocate something, create something either with the alloc method, the new method, copy, and so on and so on. So actually that'll do a little bit more than increment the reference counter. That will give you wherever that program is, the class which owns an object or something, it will basically get ownership. This is like ownership before Rust. But anyway, so we can create new things and set their reference count to 1 with these operations. There are a few others, but anyway. And then we can call retain. Now retain is when we have object A, and class A, instance A, owns an object, and it passes that over to another instance or another class or another thing, and the other thing calls retain. So if the original thing sort of allocated something, then the reference count would be 1. When this other instance retains that thing, now the reference count is incremented to 2. Okay, and this is really great when we want to pass an instance of, say, a window, in our case, from one object to another, and reference count it properly. Now we can decrement the reference count with release. Okay, so if this instance were to release its pointer, its object, whatever, then the reference count goes down by 1, but that object is not actually deleted yet. It's when everything that owns a copy of it, well, everything that owns it releases it, then the reference count goes to 0 and the underlying memory is freed, the underlying object is deleted. Okay, so this is manual reference counting. We have another option, and that is auto release. So sometimes you're running code, and auto release, by the way, is very similar to RAII. Resource acquisition is initialization, or in other words, scoped memory. It's a better way to think of it. Now with scoped memory, you'll have some code, and in that code you'll be dealing with an object, and then once that object goes out of scope, it's deleted. Now with auto release, you have what's called an auto, if I can spell, you create some sort of auto release pool. You go blah, 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 blah. Now you go and you do your thing, you make some objects, they're temporary objects, they're just meant to be scoped to this block of code. And then what we do is at the end, we call pool release. Why can I not spell release? Anyway, there we go. Something like that. Now, this pool is manually reference counted, and we make sure that it just stays within this scope. But anything which was created as an auto-release object inside this scope will automatically be freed. It'll automatically be tied to the pool. When the pool is completely released, everything that the pool owns is completely released. Now, the reason this is super important is that when you're working with Metal, you'll be creating a bunch of instances of various helper things on the fly, and all of those are auto-released. All right, so hopefully that concept makes sense. It's super important. Let's jump in and look at the boilerplate code.
Okay, so now that we've gone through the way that Cocoa apps are structured in C++, as well as the Cocoa manual and automatic memory conventions for garbage collection, I want to briefly step through this boilerplate code that I've added and then start digging into some really early Metal stuff. Now, this boilerplate code that I've got up right now is available online from Apple directly. I've sort of adapted that to my own project. This is their Metal CPP starter code. They've got a whole bunch of it. But anyway, I'm just sort of go through it. So if we go right from the top of our application, here we have our main file. This is pretty much where everything begins. Now we have these definitions as always, as normal. We've got this config, we have this app delegate, all of that. Now what we do at the start of the program is we start an auto release pool so that automatically managed memory resources will be destroyed at the end of this. I mean, I know that this is the main top level function, so they would have been destroyed anyway, but it's just best practice to always have an auto release pool for the app. So we have this app delegate, that's our main controller. Now remember, the delegate is added to the app as a means of extending its behavior. So the actual app itself, the next step application, is just a really simple thing. You make the thing, you tell it to start, you tell it to stop, that's it. If we want to implement some actual behavior, we have to set its delegate. Okay, so it seems like this is all about the app delegate. So let's have a look at the app delegate. We'll start with the header. So a nice short function name there. This is from the boilerplate code, but basically what we've got here is the app delegate manages a window, a view, MetalKit view, a device, a metal device, that's an abstraction of our GPU, and it has a view delegate. So remember, delegates can be used either to control behavior or to control view. So a delegate is just a thing that gets a message passed to it. So we can now have a look at the implementation. So if we look at the destructor of the app delegate, we have all of these things. If I go down, why is that not highlighting for me? I don't know. But anyway, if we look at this MetalKit view, for instance, this MetalKit view is constructed in the point where the application finished launching. And see here, we're constructing it with the alloc, with the allocate. So this is a manually managed object. It needs to be manually allocated and freed. So if we allocate something, we've got that happening here, then at some point we will need to release it, and the destructor is a pretty good place to do that. Okay, so remember I was saying that a delegate basically handles messages. Well, at this point, this handling of messages is done via these functions. So where am I? Just looking here, I'm not going to be going through a lot of this stuff, but we have this frame, for instance, computer graphics rectangle. This is specifying sort of the size and position of the window. And yeah, I mean, there's not much else to look at here. This is probably important, setting the pixel format and the clear color. We can change that at a later point when we get our renderer up and going and see how that affects things. I think that's probably fine, probably enough there. So again, if we go down the tree, we had that application, then the application had an app delegate, that's this one, and then we have this view delegate. So we've created this view delegate here, and then we set the MetalKit's view, set its delegate to that one. So if we were to look over here, this is the view delegate class. This is what's being created and passed over to the MetalKit view. And if we look in here, of course, we have a constructor, we have a destructor. We also have, again, a message can get passed to this delegate to say, hey, draw something. We also manage a renderer. So if we look at the view delegate, here we are. In its constructor, we construct that renderer in the initializer list up here. And then in the destructor, again, we delete it. So everything created must be destroyed. And then down here, when it comes to intercepting that draw message, all we need to do is tell the renderer class to draw that. So we've been sort of striding down our tree, and we're finally getting to the renderer. This is really cool. So the renderer is where we are actually going to be spending most of our time doing our metal programming. So I'll pop into the renderer header. As we see here, we have a constructor which takes a device, we have a destructor, we have some sort of draw routine. Now we have a device and a command queue. Now I might be getting a little bit ahead of myself, so let me give a brief description of what a command queue is. The big difference between modern graphics APIs and old ones like OpenGL is that OpenGL sort of takes drawing commands on the fly a little bit. It's not as bad as it used to be. It used to be a lot worse, but basically they take the commands one at a time, draw this thing, okay. Whereas with modern APIs, the drawing commands are sort of recorded or encoded up front. So all the commands are recorded up front, and then that is submitted to be worked on, so that by the time the GPU sees a bunch of commands, it has a guarantee that no new drawing commands are going to be thrown in there. And that means it has complete control to reorder things as optimally as possible. So that is basically what this command queue is used for. We can have one command queue for the program. It can be persistent or just sort of, well, actually, those are commands. A command queue is a little more abstract than that. The command queue is sort of a handle that the list of commands is sent to. But I think of it as the same thing. Anyway, let's head over to the renderer. And as you can see here, none of this has been implemented. So let me just work with this. We'll create the constructor first. Okay, so I'm just going to start working in my initializer list. And what I'll do is I will initialize my device, and the value that I will initialize it with is basically this pointer here. And the way we do that, if you think back to manual memory management, is with the retain function. So what that will do is that will give us a copy that will increment the reference count on that device. So we have a guarantee that so long as this renderer class does not free the device, we have a guarantee that the device pointer will be valid. Okay, so it's the job of the GPU to construct a command queue. We can go ahead and make that there. While we're at it, let's go ahead and make the destructor. Okay, excellent. So we have both of these objects. We'll just go ahead and release both of them. What we've got here, okay, I'll just talk about this really briefly. Remember that anytime we create something, we use like alloc, new, any of that. That's a manually managed object. It needs to be explicitly sort of reference counted, which is what we're doing here. But also, this is really important, any metal object is manually managed. That's the only way to get decent performance, especially for these low-level objects. So even though I haven't explicitly said new, I sort of have here, but even though I'm not explicitly using like a C++ new or allocate, this is a manually managed object and we need to release it over here. Okay, so let's get to the rendering part. So as I go ahead and do this, I'll be creating a whole bunch of objects potentially under the hood, and it will be a little too much management to keep track of them. So what I'll do is I'll scope them to this method by creating an auto release pool, releasing that pool at the end of the function. So along the way here, if I create any object, if I create any object basically, then I want that to be automatically released. by not retaining it, it will be scoped to this pool. So before, when I misspoke about the command queue, it's sort of a more subtle thing. A command queue accepts a command buffer. The command buffer is actually the list on which draw commands are encoded or recorded, and then they are submitted on the command queue. Devices can have multiple command queues for different sorts of commands. Here we're just going to use one for rendering. Okay, in addition to all of this, we have what's called a render pass, and a render pass, in rough terms, describes all of the resources which are going to be accessed or modified, read or write, in a bunch of drawing commands. Now, luckily, unlike Vulkan, we do not have to create our own render pass in this case. All we need to do is say, hey, view, which we can think of as basically representing the window, what is your current render pass? In other words, we grab a reference to the main window so that when we do our drawing stuff, that will appear on the main window, is a really brief way of visualizing it. Okay, so now what I'm going to do is there's this object called a metal command encoder, or a render command encoder. It is responsible for recording drawing commands. Yeah, it records drawing commands, and then those are submitted. Basically, it's a little funky. It's a little funky because there's this sort of indirect, it feels a little indirect. You know, every API has a part which is nice and clean and logical, and this part, I have to admit, could be more clear. But I'll try to describe it. So we have a command buffer which is ultimately going to have all of its commands written to it. The command buffer produces an encoder which consumes commands. You tell it, hey, I want to do this thing. And it's sort of indirectly, those will end up on the command buffer. What we also need is, in order to make a render command encoder, the command buffer needs to know which render pass we are going to be drawing to. Okay, so here's what we're doing. In future videos, I'll be doing more with this thing basically, but at this point, all I need to do is stop encoding straight away, because the default behavior for the render pass when we begin encoding to a render pass, the default behavior is to clear the screen. And when we got this render encoder, it basically would have cleared the screen. So we are done, we are fine. What we'll do then is we'll present to that command buffer. So ending encoding, we can visualize it as more or less throwing these commands onto the command buffer. Then the command buffer will present any graphics which were drawn. And what this actually does is it sort of encodes or it remembers a present operation to the command buffer. And then when we go ahead and commit that actually does all of the work. If I'm understanding that right, let me know if I'm not. It could be the other way around. But long story short, we spin up this command buffer to begin recording commands. We clear the screen. We present that. There we go. Okay. So fingers crossed. Let's give this a go. See what it's like. We'll just go play. Okay. Totally fine. It happens. Let's see what's wrong. So it seems as though we have an issue. I'll step through this. When I go to run this, it tells me build failed. And if I click over here, it tells me linker command failed with exit code 1, undefined symbols. That's a little strange. Now I did a little digging and I found that what that comes down to is, I believe, not having access or not compiling all the units that we need to. So if we go up here to this project and then over here to build phases, we've got link binary with libraries, this phase here. That's all good. We're going to use all of those. And then here, compile sources. Now, see, we have our source files that we need. What I'm going to do is, if we look over here, we have this app delegate and view delegate. These are both source files. They have not been included here, so I'll just grab them over. So we'll have app delegate and view delegate. I think that's fine now. It's just processing that. Let me just give that a go. All right, awesome. So build succeeded. We are good. And as we can see, we have our window, and all we're doing is clearing the screen. Now, just to confirm that this is not a fluke and it's working properly, I'll close that down. And we'll go over to, where are we? Not renderer, but view, or maybe app. Yeah, that's the one. Okay, so here we've got this clear color. And if I hover, does this work? Maybe not, that's fine. We've got these values here, so we can put in some green, run that. We've got a yellow window, that's fun. You know, what's your favorite color? Let me know. I really want to know. I don't know, give it a thing. There's a window, that's nice. What I also want to look at, this is really important to be aware of, is that Xcode's GPU debugger is really good, and it's meant to work with Metal. So if we run this program, we can see the program here, and then up on the top we've got a bunch of these little tabs. I'm just going to go to the bug spray, is it? And we can see here all of these things we're keeping track of. So that's cool. We can see like all of our performance. For instance, we can see that the time is mostly CPU, and that's literally because we set the app at 60 frames per second. What I'm really interested in is down here we have some other debug options, and we have this little M for Metal. So let me just capture the GPU workload. Yeah, capture a frame. And here we have it. Here we have our frame. We can go ahead and click on this Insights. Looks like there's just one. It says we have an empty render encoder. Yes, that's how we did it. Can click here to show performance, and it gives us a sort of some stats, which might be good to know. That's pretty cool. Look, I'm just sort of giving a brief tour. And then this is also very important. Up here we have this overview where we can see the, all the resources that we're using. And oh yeah, this also shows us the different commands we have. So we have render encoders. We also have compute blit, which is for moving memory around quickly, all these sorts of things. And we can just go over here to show dependencies. And as we make more complicated projects, this will show what we're doing. So as you can see, yeah, we pretty much just have a single render encoder. There it is. We start it up, immediately stop it, and then we present to the screen. Okay. And in the screen, we can also query which pixel format we're using and all sorts of things. It's a little weird today because we're not really doing much, but look, I mean, it's just a good thing to be aware of. So, there we have it. This has been just a little introduction to using C++ with Metal. And I hope that as this goes on, you're getting more confident using Metal and all that stuff. I can't think of how to end this, so have a great one. All the best. Bye.